So, under quality by experimental design, during this session I am going to discuss an important topic called factorial experiments, and I will discuss the details of the factorial experiments which are widely used, and one or two numerical exercises also I will try to discuss. Now, the factorial experiments are used extensively in the quality for experimental design. So, in a typical factorial experiment, what we will try to do, we try to consider all the possible treatment combinations. We have already defined what is a treatment combination, and in a given experiment you may have a large number of treatment combinations. So, what you need to do in a factorial experiment, all possible treatment combinations of the factors are represented for each complete replication of the experiment. We have already mentioned that what is this replication. So, for each complete replication, you need to consider all the possible treatment combinations of the factors. The number of treatments is equal to the product of the number of factor levels and can therefore become very large when many factors and or levels of factors need to be considered in an experiment. That means, when you suppose you have say 5 factors and each factor at 2 levels. Now, obviously, the number of treatment combinations that we will have will be far more than when you consider say the 2 factors each at 2 levels. Okay, so so there are cases when you deal with a complex situation, you may come across not only one factor, not only 2 factors, you may consider the several factors. So, for those cases, what happens if you opt for factorial experiment, the number of treatment combinations for each applications that you have to consider could be very high. In fact, the experiment size may increase exponentially with the increase in the number of factors and or the number of levels. Is it okay? There are cases where you consider say many factors, say 5, 6, even 10 factors, and each factor may have the different levels. That means, say factor 1 may have say 2 levels, whereas the factor 2 may have 3 levels or 4 levels. So, those so this case we say that essentially it is a mixed design, and the mixed design is a complex design, and usually as a first approximation what you try to do, that means you opt for a simple design, even if it may not be that accurate. So, you opt for say less number of factors, and the first the consideration is for each factor I will have the same number of levels. So, but there are certain cases where you cannot avoid consideration of say large number of factors. So, this is a major disadvantage with factorial experiments. That means, you must be very careful. Normally what is done, that you focus on only the important factors, and for that there could be some screening experiments at initial stages. That means, out of say many factors affecting the output response variable, you need to consider those factors which are very critical. Factorial experiments are widely used in numerous manufacturing and service situations when the number of factors and levels are restricted to a limited number. So, now this is the point to be noted. That means, the number of factors and levels are to be restricted to a reasonable number. So, there could be different examples, and so one particular example, let me elaborate. and you will come to know that what are the factors affecting the number of treatment combinations. Suppose there are 3 factors to be considered in an experiment. This is very common, and these 3 factors are dealing with the quality level of a component being produced on a machine. That means ultimately the response variable which you consider in the experiment is closely linked with say the quality characteristics of the particular product or the process. If the first factor, say the quality of rough stock, has 3 levels, the second factor, experience of the operator, has 4 levels, and the third factor, age of the machine, has 3 levels. Okay, so that means we are considering 3 factors. The first factor is having 3 levels, the second factor is having 4 levels, and the third factor is having 3 levels. So the factorial experiment requires 3 into 4 into 3, that is 36 treatment combinations for each replication. Okay, so the treatments are usually need to be replicated because the purpose of a factorial experiment is to ensure that any possible interaction effects between the factors can be estimated. Is it okay? So the principle of replication already we have mentioned, like a principle of randomization. So because of the replications, what happens that this will have a direct bearing on the total number of required trials. The main advantage of this experiment, that means the factorial experiment, is that it has the ability to estimate the interaction effects between the factors. I have already explained what is an interaction effect and what is the main effect. Is it okay? So in the presence of 2 or more factors, knowledge of interaction effects is of prime importance to the experimenter of the researchers. So you can prove it with several examples. So many a time you will find that your main consideration is the interaction effect, and it has been found in many cases that interaction effect is very critical, or interaction effect is very significant. If the effect of both factors on the response variable is to be determined, the interaction effects cannot be ignored. That means if there are 2 factors, factor A and factor B, so interaction effect is AB. So AB, the effect of AB on the response variable may be very significant, and that's why it cannot be ignored. If the interaction effects are present, the testing for the main effects is not necessary. Now the main effects need to be estimated when the factors are independent of one another and the interaction between the factors is not present. Is obviously, that means what we say that the effect of A, suppose there are 2 factors, factor A and factor B. So on Y is the response variable. Now what you are assuming that you have to prove with the data and its analysis, like say the effect of A, okay, on Y is significant. Similarly, the effect of B on Y is significant, but effect of A into B, that means the interaction effect, may not be significant with respect to the Y. In such cases, fewer number of trials are required to estimate the main effects to the same degree of precision. Is it okay? So you have an advantage. That means fewer number of trials you may have in your experimentation. Usually single factor experiments require more trials to achieve the same degree of precision than is obtained in typical factorial experiments. What we are saying that in many cases we go for an experiment which is referred to as one factor at a time approach. Is it okay? We have already mentioned. Now in comparison with one factor at a time approach, obviously the factorial experiment is much better. Is it okay? You can prove with the data and its analysis. Factorial experiments play an important role in exploratory studies, and these exploratory studies normally we carry out during the prototyping stage of a product. So it plays an important role in exploratory studies to determine which factors are important. By conducting experiments for a factor at several levels of other factors, the inferences from a factorial experiment are valid over a wide range of conditions. That means while you carry out a factorial experiment, you must keep in mind that whether it is the conditions which you create, whether this condition is representative of the actual the scene or actual situation or not. Okay, so your knowledge of the actual systems is very crucial in creating an experimental design. A factorial design involves typically the study of effects of two or more factors. Now let me elaborate with certain examples. So the study of effects of two or more factors that is there in any factorial design, and all possible combinations of the levels of the factors in each complete trial or replication of the experiment. Is it okay? So if factor A has alpha levels and factor B has B levels, that means A levels, not alpha. A has A number of levels and the factor B has small b number of levels. Each replication or trial of the experiment contains all the A into B treatment combinations. Okay. As an example, let us consider a factorial experiment. That is the simplest one shown in figure. I will show you the figure in the next slide. Here the factor levels are indicated as low, -1, and high, that is +1. This is just a notation. That means there are two levels of each factor. The factor could be at low level or factor could be at the high level. So the notation for low level is -1 and notation for high level is +1. And the value of the response y, okay, as a single response we are considering at the treatment combination and shown at the corners. That means it's the corners. We will show you the figure. This concept is made very clear. The value of the responses, these are the values you obtain through experimentation. That means 20, 30, 40 and 52. See, these four possible values of y you get, and these responses are plotted in figure 2. So what is this the figure 1? That means this is the figure 1. That means a two-factor factorial experiment with the response y shown at the corners. That means you have factor A and you have factor B. So what you have considered that all these two factors are very important in explaining the value of y as well as its variability. So the factor A may have two levels, that is -1 and +1. This is low, this is high. Similarly, factor B may have two levels, like say the low and high. Low is -1 and high is +1. So what you have, this is the first combination, that is low versus low. This is high versus low. This is high versus high, and this is low versus high. So all four combinations you have considered. Now when you do the experiment with this combination, you get a value of y as 20, with this combination 30, with this combination 40, and with this combination 52. Is it okay? So this is the explanation of this figure. In the next figure, figure 2, what we have considered, that means this is at the it's the low level, this is high level. Now when you consider the B at low level, you have these values, and B at low level, okay, you have these two values. Similarly, when you consider against the low value of factor A, you consider high value of factor B, and against high value of factor A, you consider the high value of factor B. What you find that there is no intersection between these two lines. In fact, they are parallel. So what you conclude that that there is the no interaction between the factors. Is it okay? So this way you establish the fact that here is a case where there is no interaction between these two factors, factor A and factor B. Now with these experimental results, the main effect and the interaction effects need to be computed. This point already we have mentioned. The procedure for computing these effects, you can just follow these steps, okay, in understanding the procedure. So now you have to compute the main effect A. So how do you compute this? Average response at high value of A minus the average response at low value of A. Is it okay? So this is so how many average response at high value of A? That means this is one value, high value of A and low value of B, high value of A, high value of B. So these are the two combinations, right? So so you take the average, that's why it is multiplied with 0.5 or half, minus average response at low value of A. So you have low value of A with low value of B, and similarly low value of A with a high value of B. So these two combinations you consider and take its average, and corresponding values you already got from this the experiment, and you use these values and get the main effects of A as 21. Okay. So same the procedure you follow to determine the main effect B. So that means the average response at high value of B minus average response at low value of B. So when how do you consider, how do you compute average response at high value of B? Again the same procedure you employ. That means B at high value, B at high value, and you consider A at low value, A at say the high value. Similarly here B, one combination, B at low level, A at low level, B at low level, A at high level. Okay, so these values you get from the experiment after you conduct the experiment, and then you substitute these values here. You use these values to get a value of the main effect B as 11. Is it okay? I think the procedure is clearly understood. Now how do you compute the interaction effect? The notation is AB. That means average A effect at B plus minus average A effect at B minus. So here A plus B plus minus A minus B plus. Is it okay? And this is A plus B minus and A minus B minus. So when you all these values you get, okay, through experimentation, and ultimately you get a value of AB, that is the interaction effect, that is 1. Okay. Now let us consider another example of two-factor factorial experiment as shown in figure 3 and figure 4. Is it okay? So as you find here in the previous case, that is the interaction effect is minimum, just 1. Now there could be cases where the interaction effect could be very significant. So here is a case, like say you consider here is a case where the interaction effect could be very significant. So here again you consider factor A and factor B. So factor A at low level as well as the high level. Similarly factor B is at low level as well as the high level. So these are the possibilities, and the value of Y for all these four combinations you get, that is 20, 40, 12 and 50. Getting my point? Now how do you conclude that there is an interaction effect? That means the factor A, low level, high level. And what do you consider? That means you consider B at low level, B at low level. Is it okay? Similarly B at high level, B at high level. And what do you find? When you draw these two lines, there is an intersection. Is it okay? So obviously if you find this sort of plot, immediately you will conclude that there is an interaction effect, and this interaction effect is very significant. Is it okay? So the following the same principles as mentioned in the previous examples. So please refer to the earlier example. The main and interaction effects of the factors A and B are computed as follows. So what you find, that means A is 30, B is minus 28 and AB is minus 29, whereas in the previous case it was simply just plus 1. So in this case the interaction effects are more significant than that in the previous examples. Okay, so what we are insisting on, that whenever you carry out say a factorial experiment, make sure that you could analyze, or you could measure, you could estimate the interaction effect, and then you conclude that whether the interaction effect is significant or not. Now let us move to a particular say the experiment which is referred to as the two-factor experiment using a completely randomized design. If you recall that we have already in the previous sessions we have referred to a completely randomized design. So the basic steps are known to you. Okay, now here what we are trying to do, we are using a two-factor experiment, okay, and with a completely randomized design. Let two factors denoted by A and B, like in the previous case, be considered in an experiment. There are small a number of levels for factor A and the small b number of levels for factor B. Already we have mentioned. Each of the total AB number of treatment is randomly assigned to the experimental units, that is following the principle of randomization. Suppose the experiment is replicated n times, yielding a total of AB into n observations. It's obvious. The model is mathematically represented as, that means yijk, y is the response variable, that is mu plus alpha I plus beta j plus alpha beta ij. These are the coefficients in fact, plus epsilon ijk, that is the error term. Okay, so I equals to 1 to A, j is equals to 1 to b, small b, and k is 1 to up to n, that means n number of replications. Okay, now so all these explanations are given over here, like yijk is the response for the ith level of factor A, the jth level of factor B, and the kth replication. Mu is the overall mean effect, alpha I is the effect of the ith level of factor A, beta j is the effect of the jth level of factor B, and alpha beta subscript ij is the effect of the interaction between factors A and B. So these are the coefficients in fact, and epsilon ijk is the random error component assumed to be normally distributed with mean 0 and constant variance sigma square. Is it okay? So the two-factor experiment using a completely randomized design, all these notations, please go through all these notations. That means these notations we have used, and for the ANOVA, that means for analysis of variance. As we have already mentioned, that any such experiment you carry out, ultimately you construct the ANOVA table, and by looking at the ANOVA table you conclude whether the model is appropriate or not. Is it okay? So that is the basic purpose. Now these are the notations we have used, like say yi dot sum of the responses for the ith level of factor B. Similarly, y dot j dot sum of the responses for the jth level of factor B. Then this is the average response for the ith level of factor A. Similarly, this is the average response for the jth level of factor B. Yij dot, this is the sum of the responses for the ith level of factor A and jth level of factor B. Okay, so these are the standard notations we use in any design of experiment, and this is the average, and this is y triple dot, that is the grand total of all observations, and this is the grand means of all observations, that means y triple dot bar. Is it okay? So this is the ultimate expressions you have, that is referred to as the grand mean for all observations. So above notations are shown also in table. Okay, so the how many factors you have, that is small a number of factors for factor capital A. Similarly, for factor capital B, you have small b number of say the levels, and then you have all these the values you get, and individually for in each cell you compute the sum. Okay, the notations are this. Okay, you just follow the kinds of notations we have been using. That is, this is the individual row sum, right? And then the average you calculate, and similarly this is the column, the summation, and against each column you have this average and the corresponding notations we have. So ultimately the grand average you get, that is y double dot bar, right? So you have to construct the table, and then what you do, you follow the standard procedure, that is the total sum of square you have to compute. The sum of squares for the main effects of factor A, SSA, and the sum of squares for the various effects of factor B, that is SSB, and the sum of squares for the subtotal between the cell totals, that is SS subtotal, are given respectively. So this is the total sum of squares. So this is the expression. This is the sum of squares for factor A. This is sum of squares for factor B, and this is sum of squares for the subtotal. And you have this correction term that is referred to as capital C, and this is the correction factor is y double dot square divided by ABN. The sum of squares due to interaction between factors A and B is given by this. That means SSAB is equals to, AB is the interaction effect, so SS subtotal minus SSA minus SSB, and the error sum of squares is SSE equal to SST minus SS subtotal. So these are the standard formulations you have, and now you have constructed the ANOVA table. So I say that you just go through all these points, right? Already, while we refer to the completely randomized the design, we have referred to all these approaches. And so the factor A could be the source of variation, factor B also could be the source of variation in Y, and the interaction between A and B, that could be also the source of variation. There must be error, and there could be the total. So you need to identify the degrees of freedom. So a number of levels is there, so that's why it is a minus 1 degrees of freedom. There are small b number of say the levels for factor B, that's why the degrees of freedom is b minus 1. So interaction between A and B, degrees of freedom is a minus 1 into b minus 1, and for the error it is ab into n minus 1, and the total is abn minus 1. Is it okay? So you compute the sum of squares applying the formula, and then you compute the means square, say mean square for A, mean square for B, mean square for AB, and mean square for say the error term. So then you compute the F statistic for A, F statistics for B, and F statistics for AB. So now you go for the hypothesis testing. So HO is alpha into beta subscript ij equals to 0 for all I, and alternative hypothesis is at least one alpha beta subscript ij is different from 0. So how do you compute the F statistics? That is FAB equals to mean square AB divided by mean square error. So if the calculated value of FAB is greater than F alpha, alpha is the level of significance, A minus 1 into B minus 1, okay, that is degrees of freedom, and again AB into n minus 1, that is the degrees of freedom for the error, the null hypothesis is rejected. So you please remember this condition, and the interactions between factors are assumed to be significant at the chosen level of significance, that is alpha. Is it okay? So this is the typical approach we have, and then what you try to do, that means you go for the estimation of, say, the confidence interval. That means 100 into 1 minus alpha percentage confidence interval for a treatment mean when factor A is at the level I and a factor B as at the level J is given by this one. Is it okay? So this is the T statistics you have, and T alpha by 2 comma AB n minus 1, the degrees of freedom, is the T value for a right tail area of alpha by 2 and AB into n minus 1 degrees of freedom. The standard deviation of the difference D between two treatment means are given by this one. Okay, so you follow these steps, and then you determine say the difference between the two treatment means is given by this. Is it okay? So this is the confidence interval, and to test significance of factor B, the statistics of FA is computed. That is this one, MSA by MSE. I have already explained this part. And similarly, 100 into 1 minus alpha % confidence interval for the mean of factor A when at level I is given by this, and for the factor A means that at intervals I1 and I2 is found from this one. Is it okay? So for factor B, the similar computations can be made for making inferences about the factor B. So here is one example. So I suggest you just go through these examples, okay, and whatever we have studied till now, right? And as far as two-factor the factorial experiment is considered, please go through this. Only thing before I close this session, I will just highlight that this sort of the questions you may have to answer, like determine the significance of interaction effect between the factors. Here the factor is temperature and pressure at the 5% level of significance. Determine the desirable settings of the temperatures and pressure if a ductile alloy is preferred. That means it is an exercise for determining the process settings, and find a 95% confidence interval for the mean ductility when the process temperature is set at this. So what is this ductility? That is the quality, and this is the temperature at this temperature and at the pressure of 150 kg per centimeter square. So these are the specific values. So this sort of the questions are raised, and you need to answer these questions. So please go through these particular typical examples, and you will come to know how to create this ANOVA table for a factorial experiment. Okay, all these details are given over here. Okay, so you refer to this particular the textbook. So I close this session.